In the previous video in this series, I made the portal of the tiny tabletop hydraulic press. In this video, I make the cylinder head, and piston. Together, they work the same as the well-known bottle jacks. A simple and I hope effective design. Seamless, thick-walled pipe is not available in my country as a private individual, unless I order 6 meters for a few €100. So I have to make do with a piece of solid 60mm round rod. That will be quite a few chips, and because I have to use a long boring bar, I will have to enjoy the mayorship of Chattertown for an hour or so. The cylinder and cylinder head are now ready in rough form. First, I want to make 2 flat surfaces on the head. These are needed to be able to attach the head later between the 2 beams of the gantry. Not visible in the video is a 1 mm deep and wide recess at the base of the thread in which the tool bit point can start cutting. Despite that, with such a simple lathe as this one, it is always very important to pay attention when cutting threads. Just one moment of inattention and the tool bit digs deep into the workpiece, snaps, or other usually irreparable misery happens. The cylinder head will be screwed onto the cylinder later. For this, I will use M48 thread with a pitch of 1 mm. Because it does not matter here, I use left-hand thread so that the thread cutter runs away from the workpiece. But first, I have to turn the outer diameter to size. I choose 47.8 mm because I want to make a tight-fitting thread. My single point threading tool has a somewhat too large point radius for this fine thread, with my tiny tool grinder that is easily adjusted. Later, the thread is sealed with an O-ring. A recess is turned in the cylinder wall for this purpose. Two precise holes of 6.1 mm at exactly 38 mm center distance are made here in the cylinder head. With pins through these holes, the head is later fixed in the gantry. This will become the piston. The diameter will be exactly 1/100th of a millimeter smaller than the inside of the cylinder. In this piston, I make a groove of 3.5 mm wide and 3.4 mm deep. An O-ring will go in there later, which should ensure a reliable seal. At the bottom of the piston, I make a shaft with M16 thread with a pitch of 1 mm. In it, accessories can be screwed later. It is important that all edges are slightly beveled and finished very smoothly. There should be no sharp transition anywhere. And here again my tiny tabletop bandsaw comes in very handy. Now that the three main parts are ready, I think it would be wise to first test whether there are any leaks. So I temporarily fill the cylinder with some oil and load it with a metric ton under my primitive little hand press. It is important to choose the maximum gap between the piston and the cylinder correctly. At the high pressure that will be applied later, if the gap is too wide, there is a risk that the nitrile rubber ring will be pressed into the gap. With the gap of 1/100th of a millimeter that I applied, that risk is absent, according to the manufacturer of the O-rings. One of the handy features of the digital readout of my load cell is that you can set it to display the maximum force in a secondary display. After more than 16 hours, under almost a ton of pressing force, almost nothing happened. This RAM is leak-free. This press has no double action. A strong tension spring will pull the piston back into the cylinder when the pressure drops. Of course, space therefore must be made in the piston and in the cylinder head. The hooks of the tension spring are attached over 2 pins, one in the cylinder head and one in the piston. Here I cut the NPT thread in the side of the cylinder head. The high pressure hose is screwed into this. This hose has a working pressure of to 630 bar and a burst pressure of 1600 bar. That is 24,000 psi. More than sufficient for the maximum 300 to 400 bar that I am going to use. The RAM is almost finished now. I still want to collect some more data, so I temporarily connect my fairly accurate digital pressure gauge to the hose inlet. Then I can measure both the pressure in the cylinder and the force exerted with my force gauge. The friction between the O-ring and the cylinder wall will probably result in a measurable loss of force. Almost 25 bar and a pressing force of only 222 kilograms. What is going on here? The surface of the cylinder is about 16 square centimeters, so the pressing force should go towards 400 kilograms. "36 bar and 339 kilograms. That should be more than 550 kilograms in the absence of friction. Is there that much friction between the O-ring and the cylinder wall? "57 bar and 548 kilograms. That could be over 900 kilograms in the absence of friction. roughly a metric ton at 100 bar. That could be 1,600 kilograms. As much as 600 kilograms of force lost to friction. I really need to investigate that further. And so, I did. I tried every suggestion. I lightly sanded the inside wall of the cylinder so that there was more oil retention. I polished the wall mirrors smooth. I used much thinner rings, 1.5 millimeters instead of 3.5 millimeters. I used the harder Shore 90 rings, but the results were more or less the same. In the end, my initial choice of 3.5 millimeter thick rings was still the best. The unexpectedly high friction coefficient between nitrile rubber and dry steel appears to be around 1 to 1.4, according to a scientific study. So maybe I just have to live with this. But you will understand, input from experts in the field of hydraulics and high pressure is very welcome in the comments. Here, I drill the holes in the gantry beams. It goes without saying that the distances between them must correspond very precisely with the holes in the cylinder head. It is always surprising how much steel comes off of apparently completely clean parts through ultrasonic cleaning. The pins are screwed into the piston and coated with metal glue over the entire length of the thread. No oil should ever be able to get through here. A simple test with some compressed air gives the expected result. Nice. For those interested in a dimensional drawing of all the parts of the cylinder, pause the video and take a screenshot. Well, the cylinder is finished and works as I hoped, although the friction is a lot higher than I initially expected. But that is not really a problem. I will only need 300 bar pressure for 3 tons of pressing force rather than 200 bar. And that's it for this time. Next video, I hope to make a prototype for a pump. I might make a few different hand pumps and eventually an electric one. I'm still thinking about it.